Hi again, everyone. My name is Julien. I will be presenting this course along with my colleague Stephen, and we have another colleague, William, helping out with running things in the background, making sure that everyone's able to that sort of thing. So the other thing I'd ask is please be aware of the terms and conditions of the Archer2 terms of and conditions of coming to one of these courses. Namely, the terms and conditions are be nice to one another, be respectful of everyone, please be polite, that sort of thing. When you logged in, you'll have noticed a poll asking you whether you've been able to log into Archer2 successfully. I will now turn off this poll because it's been on for a while. If you have not been able to access Archer2 successfully and would like to, and are not getting help from one of either Stephen, William, or myself, please do let us know in the chat. Throughout this course, Stephen and I have designed this course to be very interactive. We're both aware that LAMMPS is a huge package that's used to run a variety of things. We know full well that everyone who's attending this course will probably know at least one of the things that we're about to teach. And hopefully no one will know all of the things, because that would make for a boring course. But we also know that likelihood there are things that you as attendees know that we've never even considered, never even heard of. So we kind of wanted to have a very interactive course where people are able to talk and discuss their use of LAMMPS. And that way, I feel collaboratively we'll learn a lot more than if it's just a traditional I talk, you write, or whatever you want to call it. We've also made sure that the course material is predominantly delivered through exercises, so that you'll be running a number of simulations, LAMP simulations on Archer2, in order to really emphasize some of the points that we're trying to make. So hopefully that'll be good. It's the first time that we're running this course. So one of the things that we'd really appreciate is if at the end of the course, if you go on the Archer2 course page, there will be a link right at the bottom that says, like right here where it says register, that'll be changed to feedback. And if you could leave some feedback to let us know what we did right, what we did wrong, what we could have done better, that will be very, very helpful to us in making sure that the next time we run this course, we're able to address these things. And the final, I guess the final and most important bit of information is everything that we are teaching on this course, we have collated in the course notes. Stephen and I have put a fair amount of effort into this, and we've tried to make this as useful as possible so that even if you don't attend the course, or if, like, you know, a month further on, you've forgotten some part of the course, hopefully you can just look at these course notes, and that should be enough of a reminder sorry, what was I saying? Enough of a reminder for you to remember, oh, this is the thing that we're going to do. Regarding how the course will run, this morning is very much going to be spent looking at performance. William, Stephen, and I all work at EPCC, where we take care of the UK's national supercomputer Archer2. And as such, one of the things that we often worry about, one of the things that we often spend a lot of time trying to improve is the performance of codes. Now, LAMMPS has loads of performance capabilities, and we thought it would be a good idea to start off by discussing some of those and how to approach some of these in order to really get the most that you can, like to run your simulation in the best way possible on various systems. So we're doing that this morning. Then this afternoon, we will be looking at a couple of other topics. Namely, we'll be looking at how to measure, how to analyze certain aspects of your simulation through LAMMPS, even after your simulation's done. Mainly, this is about using the rerun command to get a bunch of information. We'll be talking about how to run replica exchange. About a year ago, when we first had this idea for the course, we noticed the replica exchange is one of those hard things to get right. So this is our attempt at doing that. And then finally, we'll discuss a bit about how to compile LAMMPS and run it through Python. And finally, we'll finish with, well, where do you go from there for any extra help there? That's the course outline, and we'll be trying to stick pretty much to the schedule. So if you're worried about breaks and things like that, just keep an eye on the schedule. We'll be sticking to that as best we can. Let's start talking a bit about LAMMPS. If you're all here, you already hopefully all know that LAMMPS is a versatile classical molecular dynamics software package that can be used to run a variety of things. Actually, I say molecular dynamics software package. I'm pretty sure at this point you can couple it with Quantum Espresso to run QMMM simulations. LAMMPS itself stands for Large Scale Atomic Molecular Massively Parallel Simulator. I suspect that they just wanted the name LAMMPS rather than work from the acronym back. It's developed by Sandia National Laboratories and also by its wide user base. Then one of the great things about LAMMPS is there's a number of user-built packages that then become available to the entire LAMMPS community, which can really help speed some things up. You can download it from this link, and I'm pretty sure that everything that we're covering today and a lot of more other information you can find in the LAMMPS user manual. Stephen disagree with me if that's not the case for his part of the course, but definitely for mine. I mean, I've not quite copied the manual, but not far. So let's quickly log in to Archer 2. I've got to share one thing while I remember. Please do let me know if you feel that I'm going through things too quickly or too slowly, and I can change the speed of either the speed at which I talk, the speed at which I go through certain topics. You should all hopefully, in a sec. Give me a sec. I will stop that and start that, and hopefully not letting me share. Anyway, there we go. So you should all hopefully be able to see my terminal. I'm currently logged into LAMMPS, so if I type ls or present working directory, you'll notice when you first log into LAMMPS, you will land in your home directory. It is in /home/project ID, which in this case is TA058/project ID/your username. So many Archer 2 accounts that I've reached the point where for new ones, I just go project ID, my initials, which is really boring, but there you go. Your usernames will differ. The way that Archer 2 is set up is there are two file systems. There is the home file system on which you land when logging in, which is backed up for recovery purposes, but is not visible to any of the compute nodes. So if you're wanting to run any simulations on Archer 2, you will need to move from the home file system to the work file system. The work file system you can get to by going to /work/your project ID, which for us is TA058, project ID /your username. That's just your, and so the work file system is a file system which is not backed up. It's really there so that you can run your simulations on the compute nodes, and then once you extract from your simulations just the most important bits of information, you can copy that across to the home file system. Most of the work that we'll be doing in this course, in fact, all of the work that we'll be doing in this course is in the work directory, so please make sure that you're in the work directory when carrying out these exercises. So usually, if you're going to run LAMMPS on Archer 2, Archer 2 has a module system. One of the modules available is a module called, is LAMMPS, and you can simply load LAMMPS module. In general, not for this course, but in general, you can simply load the LAMMPS module to get access to the LAMMPS executable. And which LMP, and yeah, that tells you exactly where the executable is stored. For this course, however, we have prepared a specific version of LAMMPS, which is somewhat different from the central install. Mainly, it has all of the Python capabilities. In order to make some of the exercises work more easily and not to have everyone need to recompile their own version of LAMMPS. We didn't install it as a central module because there's still a couple of tests that we wanted to do before doing that, but I expect that it will become a central module soon enough. Yeah, cool. Cool. So that's LAMMPS on Archer 2, and actually for this specific what we'll be doing is we will instead, whenever we use LAMMPS, we will basically load the prerequisite modules, which are module load program environment GNU. So essentially, we're going to be using the GNU compilers. We'll use the parallelized Python library, and then we'll export a number of paths to make sure that all of our versions of all of our executable and those things are available. And now if I run which LMP, it points to /work/TA058/shared blah, 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 rather than before when it pointed to, where was it? Clear? Which LAMMPS it pointed to /work/y07/shared. Said all of this, however, for most of the stuff that we'll be looking at, will be running directly to the backend. We've sort of made this course, we've attempted to make this course be as little about how to use Archer 2 and more about how to use LAMMPS on Archer 2 and in general. So hopefully you shouldn't have to look too much under the Archer 2 hood for this course. But I thought I'd preface by how do you actually run LAMMPS on Archer 2, because that's a valid question. Let me change back to the course material. Is that one. All of this information, again, is in course material. So, as I said, I kind of want this in this course to be quite interactive. So let's start with let's start the course by running a simulation. The way you can do this is if you and I'm going to be copy pasting from the course notes, so please feel free to do the same. But if you run the svn checkout command within your work directory, it will check out from the course pages. It will check out all of the exercises, and then you will have a directory called exercises. And if you go into the exercises directory, you will get 4 subdirectories, one for each of the parts of the course where we've got some exercises. We're in part 1, performance. And when you go in there, you'll notice that there are 3 files at the start. There's a file called data.ethanol, which is a LAMMPS configuration file, which shows it's the positions of it sort of defines the bonds angles, atom positions of an ethanol molecule. There's a LAMMPS input file called in.ethanol, which will run a simulation that uses the data.ethanol file. And finally, there's a Slurm submission script. So Slurm is the queue scheduler on Archer 2. To run jobs on Slurm, you can run them by using a command called sbat to submit a Slurm submission script to the queue, and that will queue up the script and then run through the script when the resources become available, and then you can it will run your job on the compute nodes. Our Slurm submission script at the start is a very simple one. There's a Slurm commands here. What do they tell you? This one tells you, well, I want the name to be called LMP Pi, which is silly because it doesn't run Pi. Cool. I want to run it on one node. It might take up to 20 minutes. It won't take up to 20 minutes. When I run it, I want it to take a budget out of this account, which is the course account. I want to run it in this bit of the queue, and I want it to run in the short queue specifically. Then these 6 lines are the 6 lines that I showed you before for making sure that you've got the correct LAMMPS environment. We're not using a multi-threaded simulation for this. And then finally, you have the actual command, which is telling you, I want this to run. srun is Slurm's sort of special equivalent to MPI run. So for any of you who've done simulations before, simulation work before, where you've used MPI run, think of srun as equivalent. It's basically the same. Want to run on a single processor, no MPI threads, and we want to run a LAMMPS executable with the input in.ethanol, and we want our log file to be log.out. That's all that this script is saying. So run it, I just need to run sbatch sub.slurm. Then if I run sq minus u user, shows that my job, which is job ID 1358055, is currently running on the standard partition. The name of the job is LMP. That's the user, and it's running for 5 seconds. It's running on this node. And if I run that again, it tells me, oh, well, it's run for 21 seconds. You can follow your jobs running by using the watch command, and then every 2 seconds, it'll update to tell you what's happening. Job is going to take a wee while because we're running it on a single processor. But please all feel free to try running these same commands. And while you're doing this, I'd like to talk a bit more about, well, about the LAMMPS input file that we're running. Also talk more about just some general information about running on Slurm. So the first thing to talk, so the first thing is why in.ethanol? It sounds a bit weird, but actually part of the reason that we're using this system is that this is a test system that I've developed to actually test large jobs. Try to make it incredibly versatile, so you can change it really quickly. But basically, what it should do is at the top, you've got a number of variables, and you can change any of those variables to change the situation under which you're running. Those variables are things like temperature in Kelvin, the pressure in atmospheres, your time steps, how often you want to modify the neighbor list. Then there's an equilibration process and then a production process. The equilibration time is about 1,000 time steps. Well, it is exactly 1,000 time steps, and then there's 10,000 time steps of production. So for a total of 11,000 steps, which is not much, right? But this is okay because this is a test system. It's really, you want something, when running performance tests, you want something that's super short, really tests out the case you're going to be simulating further down the line. How often do I want output to be printed to the log file? And then the X length, Y length, Z length defines not only the size of my simulation box, also at when I create my simulation box, at every single point along each axis, there will be a whole new ethanol molecule placed there. From memory, ethanol has 9, I think, CH3, CH2, COH, 4 plus 3 plus 3, yeah, 9. 10 atoms in it. And so if you've got 8 along the X, 8 along the Y, 8 along the Z, you've got 10 times 8 times 8 times 8 molecules, atoms within your simulation box. It's not a huge simulation box. It shouldn't take that long to run. However, for this specific case, we've made sure to set a simulation which is purposefully terrible. because we're hoping that by showing some of the techniques make this simulation, this terrible simulation, run faster, you'll learn a lot about the techniques that you can use when you've got a good simulation to make it run better. But in general, when I use this as a benchmark, I tend to not make it as terrible as this, and I can show you at the end of this session exactly what you need to change to get a sensible simulation rather than this. So the advantage of being able to quickly change your these numbers is that you're able to change your system size quite quickly. So if instead of 8, I'd instead put 10, 10, 10, then I'd be running on, what would that be? That would be, instead of 512 ethanol molecules, I'd be running 1,000 ethanol molecules. So I'd just doubled my system size, more or less, which can be quite handy when doing performance testing, especially when doing performance testing at high core counts. In general, it's really important to consider the number of particles that you have in your system versus the number of cores, the number of processors that you're attributing to your system or assigning to your system when running it. If you put too many processors and cores to work, too small a system, then you might lose a ton of time in communications. We'll talk more about a bit further down in the course. So it's important to have a system how far along has that gone? That's still running, it's nearly there. So the other thing I wanted to mention is if we look at our queue command, which tells us how our job is running, we'll see that, so this is updating happily. We've got status here is R. R stands for running. There's 3 statuses. I mean, there's more statuses than 3, but there's 3 that you'll usually see. The first one is PD, which means that your job is pending, i.e. it's in the queue and it's waiting for something to clear up. The second one is R, which is running, and the final one is CG, which stands for canceling, which means that your job is exiting. And it might be exiting because it's failed, it might be exiting because it's reached the end of the job and happy to just finish. So hopefully you've all been able to submit this job and it's either running or pending. Could I get a quick show of hands for anyone who, can everyone who's been able to submit this job put your hand up? There's a fair few of you. I guess the mention as well is if you're running this locally, the commands that I'm using are equivalent to on a local system running LMP -I in ethanol. So you should be able to copy all of this and run it locally as well if you want, and please feel free to do so. The course material has been developed with Archer 2 in mind. That doesn't mean that you have to use Archer 2 if you don't want to. Some of the later stuff might be a bit more difficult to do, but yeah, that's excellent. There's a fair few of you who have been able to. And for any of you who haven't been able to, please let me know if, please indicate in the chat whether you've not been able to because there's a problem with you getting access to Archer 2 or that sort of thing, and we're more than happy to help with that. Yeah, so the questions is I cannot access the TA058JS folder. That's absolutely, yeah, that's understandable. The TA058JS is my username. So if you look here, where it says at the very start, it says TA058JS@ln03. If you're on Archer 2, you'll have a different username here. you'll have access to a folder called /home/tao058/tao058/ your username. You will not have access to my home directory or work directory. And this is true for me as well. I don't have access to any of your Archer2 directories. So if I, let's see, if I try to go into, I don't know, MR2220, tells me, oh, sorry. If I do R2220, it'll tell me permission denied because I don't have access to that folder. If you're running locally, where can you find the where can you access the files that we're using? You should be able to, if you've got SVN installed, be able to access them by running the same SVN checkout command. And if you do not have SVN installed, give me a sec. The course material is secretly on, I mean, not so secretly actually. We're quite open about it. Yeah, no. Give me a sec. I will that for you. But yeah, it's all on GitHub. And if you just go on the GitHub page, you should be able to. Someone might very well have beaten me to it. There we go. But if you go on the GitHub page, you should be able to then just download the entire GitHub page, and in that there is a file called exercises, and that's where all of the exercises are. Cool, so my job seems to have finished running. If I look at the log.out file, it seems to have been happy to run. I noticed there's a couple of questions. Let me see. Someone's had the job failing with OMP num threads environment is not set. I've not had that. So let me check. Let me check my Slurm output, because that might just be an error that. Yeah, so you might get this error message at the start, and I think that's because there's just a typo in my script, to be honest. Yeah, that should be threads instead of thread. But it shouldn't matter because it should default to using a single thread and then just run through the things, run through the simulation anyways, which hopefully is what happened for you. Yeah, and Stephen's saying the same thing. So hopefully that answers that question. And Francisco, you have your hand up. Is that because you'd like to? Is that because you'd like to ask a question, or is that because from before? That's a fascinating one. So Kurum, could you let me know, are you running on Archer 2? Yes. And when you're trying to, oops, sorry. And when you're trying to run on Archer 2, are you running sbatch.slurm, or are you running something else? Because I don't think I got a glib error, and I think we're running in exactly the same environment and running exactly the same thing, so that's a bit weird. Before going into heavy debugging, I just wanted to talk about the first proper exercise for today's session, which is going to be, we want to look at performance for this morning's session. And performance, the performance information is always given at the end of a run at a ton of text, which gives you a ton of information about the performance of your system. So you'll notice that, for instance, in this particular job, it says about 34% of the time was spent calculating pairwise interactions, and only 5% was spent calculating bonds. K-space didn't take very long. Tons of time was spent in neighbors, and then hardly anything in comms output and modify, which kind of makes sense. I mean, comms should be 0 considering we're on a single core. Also get a ton of information about neighbor lists, neighbor builds, that sort of thing. All of this will be delving into deeper in the next section of the course, but I wanted to point out that these things are there. And then right at the end, actually a bit higher, get this information. Information tells you how many seconds it took to run. So our job here took 464 seconds to run on a single processor and to run 10,000 steps. And then it tells you the performance. So if we were to run this for an entire day, we'd get 1.86 nanoseconds. And it would take 12.9 hours to run a single nanosecond. We're doing about 21 steps per second, which is not great, but we'll improve that. Cool. And then right at the very end, you'll get a total wall time, which tells you how long the whole simulation took, including the initial part all the way, so the equilibration, the production took loads of time to run. So the first exercise we're going to do is the very first way that most people think about how can I get better performance is by going, well, why don't I throw more CPUs at it? And so, okay, let's try. The first, if you go in your sub.slurm script, you can edit things on Archer 2 using either VI or Vim. I think we've got Emacs, and I think we've also got Pico or Nano installed. My preference is VI, but free to use any of the other three. Go into this, you should be able to change srun command to change number of cores you're using from 1 to, say, 2, all the way up to 128. And so as a first exercise, what I suggest we do is we change to, yep, that works. We look at this table here, and let's have a look together at what happens as you increase the number of cores. So when you run on one processor, we know it takes about 8.5 minutes. What about 2 processors? What about 4? All the way up to 128. Now, this might take a while to do all of these together, and we've only got about 15, 20 minutes until the break. What I suggest we do instead is you just choose 1 or 2 of these and try to run them and see how they perform. Then everyone can kind of put their inputs, like you can all add the results you get to the course Etherpad. It would be excellent. So hopefully you'll have all at this stage been able to run a LAMMPS simulation on Archer 2. And if you have any questions about how to change your scripts, modify the Slurm scripts to run on more cores, please let us know and we'll chat about that. I recommend looking at 1, 2, 4, 8, 16, 32, 64, 128, just because it's a quick way of scaling up. Ooh, we've got our first 128 and 64 core results. 48 seconds and 1 minute 26. That's pretty good. That's certainly significantly better than 8 minutes. So one of the questions in the chat is, what is the minus CPUs per task used for? So when you run Slurm, you can define the number of MPI ranks you're using and the number of OpenMP threads. We'll briefly touch on this towards the end of next section. But LAMMPS also allows you to run in a hybrid MPI plus OpenMP method. And when you do that, you need to specify, or when you do that on Slurm, you will specify the number of MPI ranks which is specified by the -n command, or the more proper command is the tasks per node command. But I used an abbreviation to make it look more MPI run-like. And you also need to define the number of threads that you're using per MPI task. And the CPUs per task tells you how many, or lets you define how many threads you have per task. That answers the question. Yeah, perfect. I notice that you have your hand up. I'm unsure how to pronounce your name. I apologize. But if you would like to unmute and ask a question, please go right ahead, or you can ask the question in chat. And please, everyone, do let me know all of the questions you have. I'm here to answer them, as are Stephen and William. For an Archer 2 node, each node has 128 CPUs, so n is restricted to 128. You can use n more than 128 without, well, I mean, you just actually, Slurm will fail if you try. Though maybe if you use multi-threading, you might be able to get to 256, but from our performance tests, we found that multi-threading actually ends up making things a bit slower, so I wouldn't recommend using that. And if you want to run on more than 128 cores, you would need to then have the -n be 128, and then change the nodes count at the very top of the submission script, which wouldn't recommend. I mean, you're welcome to do, but is beyond the scope of this course. So if you were to set the number of nodes to 2, you would keep n as 128, because n tells you node tells you I want to run on 2 nodes, or 4 nodes, or whatever, however many nodes you want to run on, and n tells you, and each node has got this many cores. And I want Slurm to believe that each node has got this many cores. Hopefully that makes sense. Cool, perfect. It's great. I love that everyone. Whoops. That everyone's been sort of like together we've been able to produce a nice table, and yeah, we've got most of them done, which is excellent. Well done, everyone. Timings are all roughly where I'd expect them, which is also excellent. I'll give it another 2 more minutes before I start chatting real quick about this table. But there's already some interesting. Actually, I'll post this, and I'll ask this, and please answer it in chat. What's the one that looks weirdest about this table? Actually, there's a couple of things, but one of them just stands out as like, why is this happening? It'll list all the jobs that you currently have running, and the very first thing, which is about 8 numbers, that's your job ID. And then you can cancel it by running scancel job ID. Would it be possible to get help in the break? Yes, absolutely. Part of the reason that the break is placed there is so that if you need any further help running things, I'll certainly be staying on hand to answer any questions. Feel free to send me a direct message, and I'll look at it during the break and after you during the break. So there's already 2 answers to my question, and the one that stands out is that there's no speedups between the first and second processors, which is absolutely correct, and also super weird. You'd expect. So this exercise is what's called a strong scaling test. There's 2 ways to think about speedup. There are 2 ways to think about speedup. The first one is through strong scaling, which is the idea of if you have a problem size, a problem of size n, for molecular dynamics, the size of your problem is usually related to the number of atoms in your systems or the number of particles that you're simulating. If you have a problem of size n and you run it on a single core, then you expect that if your problem is entirely parallelizable, it will run twice as fast on 2 cores, and 4 times as fast on 4 cores, and 8 times as fast on 8 cores. However, if your system is not, if your system is not entirely parallelizable, which is often the case, then parts of your system will need to be run in serial, and part of it will need to be run in parallel. And as you increase the number of cores, the amount of time that you are stuck doing serial work becomes a bigger and bigger and bigger proportion of your total simulation time. And so you expect that as you increase the number of cores, you'll sort of get an increase in your speed will increase, and eventually taper off. And the tapering is what we're seeing when we jump from 128 to 256 cores. And what that means is essentially we've kind of reached the limit where it doesn't matter how many more cores we throw at this problem. It's not divisible enough. You can't divide this problem well enough across all of the cores you have to get a significant speed up. However, you don't expect to see that sort of thing at low core counts. And as we'll see after the break, the reason that we're seeing this strange behavior at 1 and 2 cores is because, quite frankly, the system that we are running right now is completely insane and very silly, and actually was just made for to emphasize this. And if I mean, I can actually read that. That'll be easier. If you go down a bit on this page, I've put a picture of our simulation box at the start of the simulation, and this is what it looks like. So there's the box is in each direction twice as big as it needs to, which means that we're simulating a lot of empty space. And the way that LAMMPS deals with empty space by default is not very smart. So we'll need to think about better ways of spreading the tasks between the nodes between the cores to ensure that we get a decent speed up. Well, I hope that makes sense, and we'll be talking in much more detail about this after the break. Please, as always, let me know all the questions you have. I am here to answer them, and I will be staying on during the break, so please feel free to ask any questions you want. And likewise, I don't know if even and William are, but if you ever have any questions while any of us are teaching, feel free to ask any of the three of us. We're more than happy to answer it.